chart. I want to minimize this window. Then perhaps have this here. This, and then I can go to. I know this jump to chart like that. Yeah. Hi everyone. I think I am live. Am I live? I am live. Okay, cool. So I am live and this is working. So welcome everyone to another what is it that we're working on today? Welcome everyone to another embedded workshop today. Today the intention was to work on that's misspelled. Today the intention was to work on data. To work on audio on our NRF 52840 DK. However, as I shall explain now, I ran into a problem this morning. So as I was preparing, yes, here's the development kit. So as I was preparing to connect the microphone to our development kit, I had an issue. So the kit has castellated edges, and castellated edges means it doesn't have a pin at the end. It has like a half of a circle. And what basically happened is when I tried to connect the microphone to this, I needed to solder it, but my soldering wasn't so good, so I ended up doing that to some of the pins. Now the board works. The board is going to work, and I'm probably going to be able to recover that and remove all the solder. However, the issue with that is I can't really run the demo I want because I wanted to run this PDM microphone. No, it's not a PDM. It's a I2S microphone. I wanted to run that microphone on NRF in NRF 52840. However, I can't do that, and the reason being that I can't connect it in a sane way, in a way that it just is connected all the time, and then basically that gives us an issue. However, we do have a few more things that we can't do, and then along with that, we do have this development kit, which is this STM32F4. And the interesting thing about the STM32F4 is that whereas it does not have Bluetooth, it does have audio capabilities. It has, what do we call this? It has an I2S peripheral on board, and additionally, rather than just the I2S peripheral on board, it also has an audio codec, and it also has a digital microphone. However, I wasn't prepared to do that there, but we will see. We might be able to write up some code so that it works, and maybe I should attempt that. Maybe I should attempt that. So let's just a moment. Let's perhaps, rather than be in the BLE service, let's jump out and go into Zephyr Hello World, samples Hello World, ls cut app.overlay. I don't need to mess with this because I can't actually. I don't want to mess with that because this is already proprietary code that I'm showing. So move app.overlay to app.overlay.bk. Okay, ls, and then I think let's move prj.conf to prj.conf.bk because I can't use that either. So let's just open this up, and then let's do a prj.conf. I think all I need to do here is config s is equals yes. I think that's what I need for this. I shall also, let's go and confirm. We're in the echo, we're in the I squared S sample in the echo one. This has which bolts? No, I don't want. We can use this, we will use this, but let me look at a different one. I2S codec. And this one, let's go ahead and configure I2S audio D mic. Does our STM32F4 have a D mic? Yes, it does have a D mic. It does have a D mic. I just said that it does have a D mic. But which boards is this covered on? Yeah, the DS32 overlay. Let's look. Yeah, that's fine. Yeah, that's fine. That's fine. Audio codec, yes. But I don't want the audio codec. I just want the I2S. But I don't know if I need to enable the D mic. Basically, what is happening is, let's just give a premise to the problem. What we want to do is we want to use a digital microphone. And we want to use a digital microphone, and from that digital microphone, we want to collect audio that comes in. And then based on this audio, the intention was, based on this audio, we need to run some signal processing. And the thing we were going to run very soon was just to do like an amplitude detection. So just if someone claps, sorry about that if you're using headphones, if someone claps again, it registers a thing, and then we probably toggle a LED just to show how we can use data through how do I say this? Data through audio data in the application before we start doing something like actual audio stuff. You can't use sound data without actually doing audio stuff yet, without recording the audio, without passing it through a codec and such. And I think I do have some samples today. So first of all, when you're doing something like translating real world signals into digital signals, which is called digital signal processing, which we'll deal with in another basically Streamblitz, where we'll work with DSP. If you do that, what you end up doing is you have to do some sampling of the real world data, and then you have to do some quantization, which is you basically you sample the real world data, you look at what it is, the real world data, and then you decide what it is at that time, and then you make digital projections of this data. And then once you have digital projections of this data, you can now start using them. In your digital application. Okay. And we are live. But this presents a problem, because we have one CPU on our microcontroller, and then this CPU needs to do stuff like respond to things that are happening in the analog or in the continuous signal immediately. But at the same time, it needs to be collecting the signal and using the signal, Just let me check if people got the message. Yeah. So now, the CPU we already have a problem. The CPU needs to do two things. It needs to get the data that is coming in, and it also needs to process the data that is coming in. Now, when something like that happens, you start ending up in a place where you start either you have to choose one or the other. Do you collect the data that is coming in, or do you actually process the data that you already have? And then if you collect too much and not process too much, then your processing stage is late. And then if you process too much and then you don't collect enough, what you're doing is you're basically not collecting good enough so that you can You're not collecting good enough so that you can actually represent the real world process in the microcontroller. So you're missing packets of data as you're doing your collection of data. And because you're missing packets of data, you don't have the real world data. You're making wrong decisions in your code. Now that brings us to something called DMA. And with DMA, you have something called direct DMA. Let's see, DMA computing. Yeah, so DMA basically stands for direct memory access. And this is a feature of it's a feature of computer systems where you let hardware systems, or we would call them a peripheral or something. Basically, you let data move from one place to another without the CPU being involved. Okay, so remember, if we want to say detect abnormal vibrations in a machine as it is operating, what we need to do is we need to record the vibrations, sound data, and then as we're recording the vibrations, we need to do this kind of, because the person is looking at the dashboard, and at the dashboard they need the machine to tell them, hey, there's something wrong with this part of the engine, look at it. And basically what happens is, you're either, because you have a single processor, you're either looking at the data, which means you're collecting the data coming in, or you're either processing it to make sure that there's vibrations happening and they're within scale and such. Okay, so direct memory access allows us to offload one of these tasks. So the kind of task here would be something like collecting the data and putting it in some other peripheral's memory or some memory location. So that way you can do something like your audio peripheral, I2S right now, can copy data into some memory location and put it there, and meanwhile your CPU can still be working on something else, and then when your CPU is done working with that thing, it can look at the data that has been copied in and start working on it. And your CPU basically bought time, because your CPU doesn't have to do the copying. It doesn't have to stop what it is doing to do the copying. It just, the data arrives at it, and then it does the processing. Let's read this a bit, and then we'll jump on to some sort of example, I think. So, without DMA, when the CPU is using programmed input and output, it is typically fully occupied for the entire duration of the read or the write, and thus is available to perform any other work. This is exactly the thing I was saying. You can't process the data when you also need to be fetching or sending the data. And then the thing that we said with DMA is that with DMA, the CPU initiates a transfer. Basically, the CPU tells the DMA controller, let's open a document that describes how this works so that it's easier to visualize. So the CPU talks to something called the DMA controller. We need a reference manual, ref manual. We need a ref manual, yeah. So, and in here we need to, no, I'm not going to work on the FSMC today. We're going to work on the DMA controller. So, your device, or rather your CPU is probably going, or maybe not even your CPU, your SoC, system on chip, is going to have a peripheral, or that is basically a DMA controller. And as we've learned, its DMA controller is a subsystem that allows other subsystems to copy data without the involvement of the CPU. So let's look at this example. So the DMA controller is used in order to provide high-speed data transfer between peripherals and memory, and between memory and memory. So you can copy data either from like a peripheral to memory, something like from network peripheral into memory, or other even like another example from yesterday with Andrew's conversations is you can copy from storage straight to your network interface card without going through the CPU. So data can be quickly moved by DMA without any CPU action, and this keeps the CPU resources free for other operations. The DMA controller combines a powerful dual AHB bus master architecture with independent fast in, fast out to optimize the bandwidth of the system based on a complex bus matrix architecture. So let's just look at maybe a diagram might help here. I think there's a block diagram somewhere here. Isn't there? Block diagram. System architecture. There should be. Block diagram. Yeah. No, this is what I use. System architecture. So DMA P1, DMA M1, DMA M2, DMA M3, and flash memory acceleration by APB. So whenever they say a complex bus matrix, it's this. Again, let's just go again and find out what is bus matrix computing. If you just break down all the terms, it just starts becoming quite clear. So let's look at what a bus matrix is. Bus matrix. So let's look at the CPU bus matrix. So bus matrix is basically a system of lanes. Sorry, I'm jumping to the document. All these lanes going from like the RAM to here. It's here, dude. It's here. Bus matrix. It's all these lanes that are connected in between devices. So there's something going from the GPIO DMA, and then it's going into somewhere here, and it can go to SRAM, it can go SRAM2, it can go to AHB1 peripherals, it can go HB2 peripherals. And if you look at the memory architecture, memory organization, memory map, there should be a block diagram somewhere. Why can I get where can I get a block diagram of this thing? Memory and bus architecture, system bus architecture, DMA, bus matrix. So yeah, it's basically, it describes there's two buses, AHB and APB buses. And just a moment, I should be able to find a block diagram that explains this. Block diagram, maybe not. Memory and bus architecture. Where's the block diagram for this? There is a block diagram somewhere in this document. Is it in the datasheet? Is the block diagram in the datasheet? I would know this if I saw it immediately. Yeah, exactly. So this is the block diagram I'm looking at. So all these lanes going in between, all these lanes going in between the ports and the peripherals and the other peripherals over here, and DMA and DMA1 and 2, all of these lanes of data that is going through here. These are the bus matrix. And if you see all these connections, it's either a AHB or a APB bus. That's the connection between all the items, and basically it allows communication of all of these things. So you can basically send data from extended CAN 1 all the way to GPIO port A, all through here without using the CPU. Where's the CPU? Is the CPU annotated anywhere on this thing? Where is the CPU? There should be a CPU annotated somewhere. There's a memory protection unit. Does anyone see a CPU annotation on this diagram. No CPU annotation on this diagram. Let's see. No. Oh yeah, here you go. The ARM Cortex M4 CPU. So basically, using DMA that connects. You see, DMA is connected to either the AHP bus or the APB bus. So it depends on which bus. Using DMA, you can move something like SDIO or from. Let's look at the thing we have right now. So we can move data from I2S. Let's find I2S. Does this have onboard I2S? Yes, this has onboard. Yeah, so you can move data from I2S3. And let's say you want to move audio in from I2S3 all the way out to, where would you send it? Where would you send it? Where would we want to send it? And how would we send it out? We could send it out using either SPI or something. Let's find, no, SPI is on the same thing, so that's not cool. So let's think of a peripheral that could consume I2S data. Let's basically say there's some sort of 2-wire or 3-wire communication thing on port A. You could move data all the way from I2S here. Tell me if you guys need me to zoom. So you can move data all the way from I2S3, which is here, which is the audio one, and then all the way up to GPIO port B, all through this. You see there's an APB1 here that is connected to this. And then this APB1 is connected to here to the AHB APB base matrix. And then this comes all the way here and is connected to DMA. And then from DMA, you can see there's something here that is connected from here into this bus itself. So this DMA controller can basically move data from I2S to GPIO without the involvement of the CPU. And that's basically what DMA is. It's moving data in your computer without involving the CPU in the copying of the data. And the copying of the data usually happens to be an expensive operation. Okay, cool. So before we go through all of this, let's review memory to memory DMA application. Perhaps that's gonna help us jog our memory before we take this into Zephyr, because my Zephyr preparation is for something that is basically not going to work. Documents and SD DMA. Okay, so let's get in here and walk through this code that I did, and this code is available here on GitHub, on GitHub, on my repositories. Let's see, there's something like STM. Yeah, so here's a link. There's a link here, which I'll copy and put in the chat. And you basically need either an STM32F4 to run this code, or you need some sort of emulator that's going to be able to run this code. But let's go walk through this code so that we look at it. Okay, cool. So we have all the usual cache. I think the thing we want to really look at is the main. So let's look at it. So in here we have the include for the standard integers. And then we have the STM32F4 header, which allows us to go into okay. It's basically this one. I think it's in here. It's this one. So this basically contains if I recall correctly, just registers that we're going to be using, and this is the thing that we're going to be using. Yeah, main. Okay, cool. So let's walk through this. In here, what I do is first I initialize some indicators. This is going to be at the bottom. So this is going to be just some indicators. I initialize the blue LED, the red LED, the orange LED and the green LED, and I'm going to be using them later to show what is happening, okay? Because DMA works really fast, okay? And then there's a busy wait time. I think this is a function that this is going to be this is just something that waits for whatever time times 16,000, okay? It just does a no operation. And then I define a buffer size, which is 32-bit bytes, okay? And then I define a source buffer and a destination buffer, and I initialize our destination buffer with all zeros, and then I initialize our indicators, and then let's go here, and then I fill our source buffer with so the size of the buffer is 24, and in each buffer I put in each byte, which is 32-bit byte. In each 32-bit byte, I put in a number from 0 all the way to buffer size, all the way to 1 less than buffer size, basically. I'm going 0, and then I put in 1, and then all the way to like 23, because 0 to 23 is 24. Okay, cool. And then what I do here is I enable DMA2. Enable DMA2. So this is just enabling this. Let's look at DMA here. Are in search? No, this is the wrong document. This is the wrong document. So let's go back here. DMA, functional description. So what we do here is we enable the DMA stream. Yeah, we enable the DMA stream. We enable the DMA2, and the reason we're using DMA2 is because DMA2 is the one that can go from memory to memory. Here it's described here. So one of them can do memory to memory, and the other one cannot do memory to memory. Just a moment. Yeah. Wait. So DMA, it's somewhere in here. But basically, one of them can do memory to memory, and the other one cannot do memory to memory because it's not connected to the right places. Yeah, the DMA controller provides two AHB bus master ports and the HB memory port intended to be connected to memories. The HB peripheral port intended to be connected to peripherals. However, to allow memory-to-memory transfers, the HB peripheral port must also have access to the memories. So you also DMA1, see DMA1 here to DMA2 to peripherals, and DMA1 to AHB2 peripherals and to AHB2 peripherals. And then you will see that one of them, the DMA1 controller AHB peripheral port is not connected to the bus matrix like the DMA2 controller. As a result, only DMA2 control streams are able to perform memory-to-memory transfers. And right now we're doing memory-to-memory transfer because that's the easiest way. Okay, so let's look at it. So what we do here is we're now setting up the DMA stream. So we disable the stream, and then while the stream is disabled, we set the stream to be enabled. We disable the stream and we wait until it's disabled. The reason we do this is so that before we go to running all of these things, we need to how do I say it? Before you start using a peripheral, you need to disable it, and then you need to do, let me show you here. It's easier to understand when we're looking at DMA registers. Quite a few of the registers, the value does not take effect unless unless the DMA thing is disabled, is basically what I'm saying. So let's look at StreamX configuration. Yeah. Once the StreamX configuration, that's too low. That's too low. So is there something in the... But basically, you can't configure a DMA stream while the DMA stream is enabled. That's basically why we disable the DMA stream, and then we wait until it is disabled. And then once it has been disabled, I need to can make provide compile commands. I'm trying to see if I can get compile commands generated so that these are found basically. Okay, but they do exist. Just that my language server, my LSP is not finding them, so they do exist. Sorry about that. So, and then we set the addresses, and what we're doing here is we're setting the PAR and the MOAR. Let's look at this. What do they mean in the reference manual? PAR and MOAR. Yeah, so PAR. What are we setting in? We're setting in the stream. We're configuring the stream. PAR and POAR. So that's going to be the source and the destination. Yeah, bit 19 bit. Come on. Come on. Let's find this. This is a problem of preparing to do something in Zephyr, and then we have to do something in here. So PAR, DMA, yeah, PAR. DMA PAR. So PAR is the peripheral address register, and then MOAR is the memory address register. So what we're writing is the source buffer, we put it in the peripheral address register, and then the destination buffer, we put it in the memory address register. And this is just like we are pointing. We say, hey, fetch this data from the source buffer, take this data to the destination buffer. And then we declare the number of items in the buffers, so buffer size. And then we set the priority of the DMA transfer, because if there's another transfer in contention, it's going to be and then we set peripheral increment and memory increment. The reason we set this is so that once DMA, sometimes you can use DMA where you're copying and overwriting, copying from this place and overwriting this place, copying from this place and overwriting this place, copying from this place and then overwriting this place. So you're basically implementing some sort of circular buffer with that. But in our case, we want to copy, and because we want to copy a fixed size of items, we want to copy each one of them, and then not copy. The first one should go to the first address, and the second one should go to the second address, and the second and the third one and the fourth one, and so on and so on and so on and so forth. And also the source addresses. Like the first one should come from the first source address, the second one should come from the second source address, and and so on and so forth. And then we declare M size, and which is basically the same thing. I think let's just look again. M size, yeah. So memory data size, peripheral data size. Remember, we're doing one side to another, one size to another. And then M inc is memory increment, and P inc is peripheral increment. So from where you're copying, increment like this. And then you can also have DMA act like a circular buffer and all of those things and such. There's quite a lot of there's quite a few conveniences built into for you. Okay, cool. And then MOAR and POAR are here, peripheral address register, SPAR. And this is base address of the peripheral data register from or to which the data are read or written. Okay? And then memory address register is the same thing. The base address of the memory area from or to. Remember, if you're doing memory to memory, one of them will be from, one of them will be to. And then if you're doing peripheral to memory, one of them will be from, and then the other one will be to. And I don't even remember if we can do. Can we do? No, that's silly. Can we do peripheral to peripheral? It doesn't sound like we can. But then it doesn't sound like we can. Peripheral to memory, memory to memory to peripheral, memory to memory. Well, you can sort of sneak by doing peripheral to memory and then lash that on memory to peripheral, and then basically done. Peripheral to memory, peripheral to peripheral. Oof, I've said so many words today. Okay, and then after that we enable the TCIe bit, which is going to be the TCIe is going to be what is in stream O. Configuration TCIe. I saw it here just now. Okay, transfer complete interrupt enable. So we enable an interrupt to fire at the moment the transfer is completed. Okay, so ping us when the transfer is done. Okay, and then we set our blue to that we are starting, and then we busy wait for 200 whatevers, for 200 clock cycles for whatever, and then LIFCR is gonna be what? Low interrupt clear register, LIFCR, and then we set what? DMA LIFCR CTCIF. So stream X clear transfer complete flag. So we clear the transfer complete flag before we start completing, in case another transfer was happening and we don't know. So we say, okay, we are going to clear this, and then we will watch this status register, and when this status register changes, we know it's cleared, because we know the transfer is completed because we started by clearing it. We started by making it say it's not complete. Okay, cool. And then in here, we're going to basically enable the stream. And then let's look at what our DMA stream or IRQ handler does. So here we start the orange LED, and then we busy wait for 200, because if we do not busy wait for 200, this will all finish so quickly that it'll basically not matter. And that's basically, and then we wait for 200, and then we check if the data was copied. Okay, if the data was copied, green means that we finished, and then I think 14 is something like, what is 14? 14 is red, means it failed. Okay, cool. So I think we can actually do this. Readme. What do I do? Okay, make clean. Okay, make. Okay, that's built, and I think I can use. I do have a program. Yeah, I do have something like which flash. Yeah. What does that? Cut flash cut flush SF4. Okay, cut yeah. Anyways, so let's look at nvim home. No, cut home Zach documents. I'm probably quite closer than just going from, and then open OCD, and then let's look at flush. What do you do? Okay, you need an ELF file. ls build, you need an ELF file. m2m DMA ELF. Okay. I shall connect this guy. Yeah, I'll remove this. I shall connect this guy. Okay, and then flash top, and then it's gonna be build. It's red tab, and then m tab elf tab. Okay. Not good. ls USB. When did my device change? When did my device change? It shouldn't. Why are you using? Do I need to use a custom? It should not. Let's see. I need to check this guy. Let's check that OpenOCD file. I know what is happening. Where is that OpenOCD file? Okay. I think I know what is happening. CD OpenOCD. Clear. Yes, I think I know what is happening. Git ls-a git diff. Vim, what file is this? It's TM32 ST link F4 disco. LS. And Vim, you can come up here if you want. You can come. And then here. Yeah, this should work now. No, this should work. And then that, and then that. And then we'll go eng, and then we'll go TM32 for DMA. And then let's do that. And then I shall do that. It's red. I can see the reflection. And then let's try and just flash this. Yeah, it's flashing. And what happened? Okay. Go. Ooh. No. Yeah. ST. Open SCD. Git diff. Sudo open SCD. Briefly. Target remote location, monitor init, monitor write image, flash erase, sudo kill open OCD2, yeah, it's fine, sudo it's fine. Is it because this one expects sudo? No, that's not the reason. What did I do? How did I manage this? How did I manage this? How did I break this? I thought that was the only thing. Let's look at what error we're seeing. Clear. Is there something we're doing here that is making us use JTAG rather than... There's nothing. There should be nothing. There should be nothing. Just a moment. Let's try a different one. I should have a different one here. Something in some setup is wrong. And I can't figure it out. I don't know. This seems like one of those streams when... Okay. It's definitely something I changed in here. So... What did I change? What would I have changed here? Flash F4. Okay. Shift key. And then in here, let's not go target extended remote. Yeah. It's that, and then that. Isn't that what we added before? Monitor reset halt was there. Monitor init, monitor reset halt. So this one's going to be X. X monitor init. Is init what? That's what monitor init. It's load. That was load. Is what? Monitor reset halt. We removed that one, so target remote localhost init, and then target remote I see what's happening here. Target remote local host 3333. But wait a minute, why is that 3333? Which file is this? Flash F4, yeah. Okay. Flash F4 build LF. Not that. Okay, let's look at the diff still. So we've put that back in. So sudo where is that sudo? Number 26. Right. Starting OpenOCD in the background. Yeah. Sudo. let's see if this is the issue. Yeah, sudo, wait briefly, blah blah blah, blah blah blah. That really is all the changes. And that's 332. Why is that 332? Oh yeah, that's just the one I copied over now. You don't know. Does anyone know how to fix this? Of course I am a human, man. It's funny when the computer needs me to confirm that I am a computer. Maybe I am a computer. Do you want me to run the OpenOCD thing on its own self? You see, this is a problem of getting too used to being in Zephyr land. Unless this doesn't make sense. Am I supposed to do that? Open OCD-F SD-link config. Oh, I'm gonna feel so dumb when that's the solution. See, I don't think so. Oh, basically what happened, I lost it again. I don't know. And I don't know why it's going to that. VJ28. VJ28. No, VJ37. Okay. Cool. So it seems I might have to update the update. Oh my word. This is a problem. I might have to update the software on my Flash. Wait. Flash normal elf from Cepha. Flash external elf using West Flash. Where's West? Where's West? Do I have West somewhere? Do I have West somewhere? Activate. Clear. West Flash. Dash help. CD. Yeah, Zephyr project. Okay, so West Flash dash elf dash file. Then we're gonna do documents. Documents and STM32 build. Dash build dash dir. Okay, cool. So it seems I need to debug a bit more. For some reason, I cannot run that example, which was running just right now, quite simply. And I have no idea what I'm doing wrong I have no idea what I am doing wrong so that my OpenOCD is not working. So I don't know why we're getting this error. I did do some experiments where I started using this as a debugger, and I might have changed things on here, but I don't know what I would have changed so much that it would make it different for this. Anyways, thank you for bearing with me today. This has been quite a difficult stream. I'll work on it a bit more, and then we'll come back and do it again tomorrow, and then we'll see what happens. Thank you for hanging out. That was a cool thing. This is real development. Sometimes it doesn't work out, but this is what we get. Thank you, and cheers for hanging out today. Let's see. Unless you have any questions, and if you do have any questions, then you can post them up, and we can get them going. No questions? No questions. Yeah, so I don't like that.